Okay, let's go ahead and get started. Here, I'm handing out the next problem set. Just a word of advice. You have 2 weeks to do this problem set because there's no lecture next week because of reading period. This problem set is therefore a little bit longer. So I recommend not leaving it until the last day or two. It's an interesting problem set. A lot of good physics on this problem set. So hopefully you should have some fun with that. Let's see. No other administrative announcements, so let's go ahead and start doing some physics. So let me just remind you of where we left off last class. So last class we started discussing how to do physics in curved spacetime. So the basic strategy for doing physics in curved spacetime is that you take your favorite law of physics in flat space, in Minkowski space, and then you covariantize it in the obvious manner, meaning you replace partial derivatives with covariant derivatives, Minkowski metric with curved metric, and so on and so forth. And the basic observation that we made about physics in curved space is that objects which are not acted on by external forces will travel on a geodesic. They will travel on lines that are as straight as possible given the curvature of the geometry. So we then asked, how is it that the curvature of spacetime could account for the effect of gravity? And so we asked, can this reproduce the equation of motion of Newton's law of gravity? So x double dot is equal to minus the gradient of the Newtonian potential. And the answer was yes. If you imagine a particle traveling through a spacetime which is close to, but not exactly, Minkowski space, with a metric that differs from that of Minkowski space only through the dt squared element, where phi here is the gravitational potential, then in fact the geodesic equation, in the limit where phi is very small, just reduces down to Newton's law describing the motion of objects moving in a gravitational field. So we saw that, in fact, if Newton had known Riemannian geometry and been very, very clever, he might have been able to come up with the theory of general relativity, or at least the basic insight that instead of thinking of gravity as due to an external force acting on an object, you could also think of gravity just as a feature of spacetime itself, namely the curvature of spacetime, and Newton's law, which says that objects, that F equals ma, where F is the gravitational force, can just be interpreted as coming from the geodesic equation in curved spacetime, at least for objects that are moving very slowly, and for gravitational fields that are independent of time and that are relatively weak, in a sense which we'll make precise later on in this course. So the moral of this story is that the metric of spacetime should be thought of as analogous to the gravitational field in Newtonian, the gravitational potential in the Newtonian formulation of gravity. And so the next question we ask is, what is the equation of motion that allows us to determine the gravitational field, which is to say the metric, in terms of whatever matter and energy sources are present? And the answer that we saw, so we gave a simple answer to this question in the case where there are no matter fields present. So we wrote down Einstein's equation in vacuum, which is to say when there are no sources present. And our basic principle was that it had to be an equation which was A, a tensor equation, and B, second order in derivatives of the metric. And the only possible tensor that one can construct with this property is the Riemann tensor. So the equation of motion for the metric of space-time has to be some equation involving the Riemann tensor. And if you're looking for Einstein's equations in vacuum, that's the only thing that can appear in that equation, because there's no matter or energy to act as a source for the curvature of space-time. And we made a guess for what the right equation was. And what we'll see, okay, and we checked that indeed this equation, if you work it out carefully, will lead to Newton's law. Did we check that last time? Well, we're going to do it. Did we do it last time? Yes. We checked that this equation of motion will lead to, in the limit where the metric is equal to this guy up here, it just leads to Laplace's equation for the gravitational potential phi, which is the usual source-free Newton's equation for the gravitational potential in Newtonian gravity. We didn't do that? Okay, I forgot whether we did that last time. Well, the question then, okay, let me rephrase this. I forgot whether, so last time when I taught the course, I did it first in the vacuum case and then again in the matter case. So, okay, the question that we have, does Einstein's equation in vacuum lead to the equation of motion of Newtonian gravity in the limit where the metric is given by this Newtonian form that I've written here, where phi is very small. So that's one question that we would like to answer, and that we will answer today. And the second question is how we incorporate sources. So how does matter or energy, which is present in space, lead to the curvature of space-time? And so that is the question that we will answer first before answering the first question of how Einstein's equation, r mu nu or g mu nu equals 0, will lead to the equation of motion of Newtonian gravity. And once we've checked that, we will have completed our formulation of general relativity and written down the equations of motion for the curvature of space-time that correctly reproduce all of the laws of gravity that we encountered, that we know and love from Newtonian physics. So before I dive into answering these two questions, let me pause and see if there are any questions. No questions? Okay. Today is a good lecture. Today we learn the equations of motion of general relativity in all of their full glory. So the first thing that I would like to answer is the second question. How do we incorporate the sources that will be present on the right-hand side of Einstein's equation? Well, we decided last time that we needed our sources to be represented by a symmetric 0, 2 tensor. And so we introduced the stress tensor, T mu nu, which is the flux of form momentum P mu across a surface of constant x mu, x nu. So, for example, T00 is the energy density, T0I is the energy shear, Ti0 is the momentum density, and Tij is the momentum shear. And decided that this looked like the right quantity to appear as a source in Einstein's equations. And I started last time of introducing a particular type of matter, namely that of a perfect fluid, and describing to you what the stress tensor looked like in the case of a perfect fluid. So a perfect fluid is what you think of as a perfect fluid. It's parameterized by two numbers, an energy density and a pressure density. And if the fluid is moving in some way, then it's also parameterized by a vector, which is the forward velocity of the fluid. And this vector is, of course, a function of spacetime, because you could have one bit of the fluid over here, which is moving in a different way from another bit of the fluid on the other side of the room. And much of the matter that we will consider in this course will be modeled as a perfect fluid. Now, of course, not all matter is a perfect fluid, but for the purposes of this course, we will at least make the approximation in many cases where the matter that we're looking at is a perfect fluid. So, the stress tensor of a perfect fluid, we argued last time, has to take the form of P plus rho times U mu U nu plus P times G mu nu. So why did it have to take this form? Well, when the fluid is not moving, the stress tensor just has to be a diagonal matrix because there's no shear forces anywhere. And the diagonal entries have to be rho, P, P, P. And this was the only quantity that we could build out of the forward velocity U and the metric G mu nu, which had the property that it was a symmetric 0-2 tensor and also reduced down to this diagonal form when the fluid was not moving. So are there any questions on that? Okay. So I would now like just to bring this discussion down to earth a little bit and just tell you a little bit more about perfect fluids and what they look like and describe them just in a little bit more detail to you so you can understand the context in which we'll be using them later on in this course. So now, this is not a class in fluid mechanics. It's not a class in mechanics at all. So I'm just going to quote for you a few properties of these perfect fluids. And these are properties that you probably already know, or if you don't know, are actually rather simple to understand. So the first thing that I would like to point out is that for many perfect fluids, P and rho are related in a simple way. And in particular, there's an equation which relates P and rho, which is known as the equation of state. For an ideal gas, for example, there are various equations that relate the energy density and the pressure density. And the simplest sort of equation of state is the equation that we will consider in this class, which is linear, where the pressure is proportional to the energy density, with some constant of proportionality W that's just a number that is known as the equation of state parameter. Okay, that's not a very creative name for the parameter W, but I've never actually seen it called anything else. So let me give you an example of three sorts of perfect fluids, two of which you already know about and one of which will probably be new. And these are the three sorts of matter that we will most commonly discuss in this course. So the simplest sort of perfect fluid that you could imagine would be one which is pressureless, namely where W is equal to 0. So then you have a pressureless fluid. So, which is to say, a fluid which has only an energy density rho. So what is this? This just describes some matter with some 4 velocity, u mu, and some energy density, rho. And we usually give a name to this sort of matter. We often call it dust. This is more of a historical name, but dust indeed is an example of a material with this property that it can be treated as a fluid in the sense that it has a 4 velocity with an energy density and no pressure. When you think of normal matter, in the context of general relativity, you're thinking about dust, usually. Now, you might then ask, what sort of materials do you know of which have an energy density, have a pressure density in addition to an energy density? Well, the other simple example that you know about is a material which has W equals to 1/3, i.e. a pressure which is equal to 1/3 the energy density. So this is, in fact, the equation of state of a gas of massless particles. So of a gas of photons, for example, or any other massless particles. In your electromagnetism classes, or in one of your quantum mechanics or statistical mechanics classes, you might have actually computed this equation of state of a gas of photons. So in your StatMat classes, did you compute this equation of state? Or did you study this equation of state? So you saw, if you did this in your StatMat class, that the pressure that a gas of photons has a very simple relationship between the pressure and the energy density. And so this is the type of matter that we usually just call radiation. So you might ask, why is it in this course that we will even think about considering radiation as a source of the curvature of spacetime? Because most of the matter in the universe appears to be dust, stars, galaxies, all that's dust as far as we're concerned. So why would we consider radiation? Well, it turns out that in the very early universe, in fact, there was a period where most of the energy, or a large fraction of the energy and pressure of the matter terms in space were dominated by radiation. So as we'll see in our discussion of cosmology, even though right now radiation makes up a very small fraction of the energy density of the universe, at very early times it made up a sizable fraction of the energy density of the universe. And so, in fact, it's a very important contribution that you have to take into account if you want to study the evolution of the universe according to general relativity at early times. So, I told you that I would give you 2 examples of perfect fluids that you know very well, and another example that you don't know well at all. So, let me now tell you of an example that you don't know. So, I would like to start by motivating this by considering this formula that I have written here for the stress tensor. So, let's stare at that formula for a second. Now, usually we consider fluids which have a positive pressure. Okay. We don't really know very well how to imagine a fluid which has a negative pressure. But if there were such a fluid, and if you could imagine that you had a fluid with P equals to minus rho, then there would be a remarkable simplification in this equation. And what you would find is that the stress tensor is just proportional to the metric. And in particular, it would be independent of the 4 velocity of the fluid. So this would be some sort of very strange kind of matter term that could appear as a source in Einstein's equation, which you could think of as a fluid, but it's independent of the 4 velocity of the fluid, and it's just proportional to the metric. So in a sense, it's more like a property of spacetime itself than it is any sort of perfect fluid. So this is a sort of matter term that we will consider very much in this course. So this, in the language that we had above, would have W equals to minus 1, so that P is equal to minus rho. And the stress tensor will be minus rho times G mu nu. Did I get a minus sign wrong somewhere in my notes? I think I must have gotten a minus sign wrong somewhere in my notes. Anyway, the stress tensor is proportional. Okay, now my computer stopped working. There we go. The stress tensor is proportional to G mu nu. The reason why I forgot the relative sign there is that we usually have a different name for this quantity when we consider the sort of matter with P equals minus rho. We usually call that quantity lambda, and lambda is referred to as a cosmological constant, or alternatively as vacuum energy. So this is a very special sort of matter. It's sort of qualitatively different from the other sorts of matter that we will consider in this course, in that we don't have any examples of matter with this equation of state here on Earth for us to study. And so to postulate this type of matter that would appear in Einstein's equations would be quite a bit of a leap. It would be postulating a new sort of matter that would appear as a source term in general relativity that, in fact, we haven't observed here on Earth. In fact, we would not be the first people to postulate the existence of such a type of matter. Einstein postulated it in the very early days of general relativity. He then quickly discarded it and decided that he was wrong, but it turned out that he was probably right. And in fact, there are a lot of very interesting observations in cosmology and astrophysics which indicate that there is probably a cosmological constant or something like it. And I've also referred to this constant as vacuum energy because we often think of this type of matter as a property of space-time itself. And the reason why it will be called vacuum energy will become very apparent, probably not this class, but next class. And I think the existence and the properties of the cosmological constant are one of the main mysteries, unsolved mysteries remaining in the theory of general relativity. And so it's something that we'll spend a fair amount of time discussing as this course proceeds. Okay, so these are three different types of perfect fluid matter that we will consider in this course. Let me now tell you a few more of their properties. But before I do so, let me pause and see if there are any questions. Yes?
How do you express dark matter in terms of
Well, you need to decide what sort of matter your dark matter is. The current best model of the universe is the so-called lambda CDM model, where, as you probably have heard, the visible matter that we see around us accounts for only 4% of the total matter in the universe. The other 96% has to be counted for in some other way. The lambda CDM, the abbreviations lambda CDM stand for lambda, as I have drawn it here, and CDM standing for cold dark matter. Cold dark matter just refers to the equation of state of the dark matter, and lambda refers to the cosmological constant. So we'll discuss that in great detail when we come to cosmology, which will be later on in the course. So yes, it's not an accident that I've introduced these three types of matter. All three of them appear as actual source terms in the equations of motion of our universe. Okay. Any other questions? Good question? I mean, it's really a fascinating time to be studying this because, you know, when I took general relativity, the cosmological constant wasn't even introduced in the course in general relativity because everyone assumed that there was no cosmological constant. You know, so this is something that is really changing rapidly, and the fact that there's a cosmological constant, or at least something which looks very much like a cosmological constant, is something that really only in the last 15 years is something that we've really only understood in the last 15 years or so. So we're really in an era of precision cosmology, which makes this subject very exciting. And so we'll spend a good deal of time on cosmology later on in this course. But before doing that, we need to understand general relativity. So the final property, and in some ways the most important property of a perfect fluid, at least for the purposes of this lecture, is that the stress tensor of a perfect fluid obeys an additional differential equation which incorporates the idea of the conservation of matter and energy locally. So, how is this equation written? Well, the covariant derivative of the stress tensor, where you contract one of the indices of the stress tensor with the derivative, is equal to 0. And this is the relativistic version of the equation which says that the stress energy is conserved. So I think it's instructive to work out a few specific instances of this equation in flat space, and just to check that this gives you the usual conservation laws that you're probably already familiar with for a fluid. So this equation gives what we think of as the usual equations of motion of a fluid. So, for example, it will reproduce the continuity equation. So if you consider a fluid which is moving very slow compared to the speed of light, then the zero component of this equation, where you set nu equals to 0, will say something like the fact that the time derivative of t00, which is to say the time derivative of the energy density, is equal to the divergence of the energy density times the velocity. So here I've neglected all of the pressure terms and set the velocity to be small compared to the speed of light. But you can check that in this limit, this equation for the conservation of the stress energy tensor just leads to the usual continuity equation. And I'm sure you've encountered the continuity equation before in your lives. It just says that if you have some matter distribution with some energy density rho, that is moving with some velocity v, then the change in the energy density with respect to time can be computed by looking at the total outflow of energy density from a given point at that time. So this first term here just is the total change in the energy density here. And this here, we're looking at the spatial outflow or inflow of energy coming from a given point in space-time. So surely in your electromagnetism classes, for example, you saw this. It's the quantity in the small parentheses here is also, of course, known as the current in electromagnetism. And this would be the equation for the conservation of the current. Have you guys seen this before? Okay. If you have not seen it before, you are not going to learn about it in this class, because this is a class on general relativity and not a class on mechanics, continuum mechanics. But this is one of the basic conservation laws that a fluid must obey in order for energy to be conserved. So this is the statement that locally energy is conserved. There's also a statement that locally pressure is conserved, which is found by taking the nu being one of the spatial directions rather than the time direction in this continuity equation. That gives you what's known as the Euler equation. Those of you who are taking fluid mechanics, I'm sure, have seen the Euler equation many times. I won't bother to go through it here. I can never exactly remember how it goes. But it's another one of the equations of motion of a fluid, which is reproduced by this conservation equation. Okay. So, given everything that we have said about the stress tensor, it's now, I think, time to ask what is the correct equation of motion of general relativity when you have sources present. So let me remind you that when T mu nu is equal to 0, namely there are no sources present, we decided that the equation of motion which made most sense was the equation where r mu nu was equal to 0. Now when r mu nu is equal to 0, its trace is equal to 0. So we could just as well have set g mu nu, which was r mu nu minus 1/2 the metric times the trace of the Ricci tensor, namely the Ricci scalar, equal to 0. So the question then is, what is the correct equation of motion when T mu nu is not equal to 0? Well, the first thing that I would like to point out is that we want to write down some equation where we have the curvature of space-time on one side and the stress-energy tensor on the other side of the equation. But, so you might naturally try and write down an equation like r mu nu is equal to T mu nu with some constant of proportionality kappa that we're going to have to determine. But if you stare at this equation for a second, and you remember this conservation equation that I wrote up above, then you'll see that this can't be right. Since the right-hand side of this equation obeys a conservation law, whereas the left-hand side does not. So if this were the equation of motion of general relativity, it would imply that in some cases stress energy is not conserved, and of course the conservation of mass and energy is a principle that we would like to preserve in the theory of general relativity. However, if you paid careful attention in my lecture on curvature, you will remember that the Einstein tensor, this funny combination of the Ricci tensor and the Ricci scalar times the metric, is conserved in the sense that if you take the derivative of the Einstein tensor, contract two of the indices and set it equal to 0, you get 0. And in fact, the Einstein tensor is the unique symmetric 0-2 tensor that you can construct out of second derivatives of the metric, which has this property. So the correct equation must be the equation g mu nu is equal to kappa times T mu nu, where kappa is some constant of proportionality that we're going to determine. Any questions on that? This is a very important argument, and I think this is the argument that Einstein originally used to formulate the equations of motion of general relativity. Next class, we'll come up with a different argument based on action principles, but I think this is probably, at least historically, the best way of understanding the origin of the equations of motion of general relativity. Any questions on this? I see a few very puzzled or profound looks. Okay. Well, we're going to spend a little bit of time processing this equation and thinking about this equation. And the first thing that we would like to ask about this equation, well, we're trying to come up with a new theory of gravity to replace Newtonian gravity. So the first thing we better ask about this equation is whether this reproduces everything that we know and love about Newtonian gravity in the appropriate limit. So does this reproduce the equation of motion of Newtonian gravity, which determines the Newtonian gravitational potential in terms of the sources which are present, in the appropriate regime, namely in the approximation where the metric is very weakly curved and close to flat. And so I remind you that Newtonian gravity is described, as we saw last class, by a metric which is given by the Minkowski metric with a correction term that is proportional to minus 2 phi in the TT component of the metric. And so our question is whether, if we just have some matter distribution given by some function rho of x, does the Einstein equation, g mu nu equals a constant times t mu nu, reproduce the usual familiar equation of motion of Newtonian gravity? This is probably the most important check that general relativity will reproduce all of the familiar rules of classical Newtonian physics, which have been verified so well. So this is the first well, maybe the second if you include our discussion of the geodesic equation. So this is the next non-trivial check of the consistency of general relativity as a theory of gravity. So what we want to do is compare Einstein's equation to the boxed version of Newton's equation. The left-hand side of Einstein's equation, g mu nu, will turn into something quadratic in the derivatives of the Newtonian potential phi, and the right-hand side, as we described, will give us the energy density. And in particular, in Newtonian gravity, the equation grad squared phi is 4 pi g rho is the equation that describes the Newtonian potential just for some matter distribution, i.e. dust with no pressure, so that we'll be taking dust in its rest frame. I guess I'll write it with lower indices. So that the stress tensor will be zeros everywhere except for the 0, 0 component, which will be proportional to rho. So is the question clear here? So our strategy now is going to be to write out Einstein's equation, and we're going to work in the approximation where the metric is very close to flat, so that, and then we're going to keep all of the we're going to expand in powers of phi, and on the left-hand side of Einstein's equation, we're going to keep the term of order phi and hope that it's the Laplacian of phi, and then work the 0th order in phi on the right-hand side and hope that it's proportional to rho. So let's see how that works. So we're working here with Einstein's equation, G mu nu is kappa T mu nu. So, as I said, the first thing that we can notice about this is that you can take the trace of both sides to get an equation for the Ricci scalar R. So let's go ahead and do that. So G mu nu is R mu nu minus 1/2 the metric times the Ricci scalar. So that was kappa times T mu nu. So let's give ourselves a little bit of room here. So let's take the trace of both sides. So that says that R, which is the trace of the Ricci tensor, is minus 1/2 the trace of the metric, which is 4, just because we live in 4 dimensions. So minus 2 times R is equal to kappa times the trace of the stress tensor, which I'll call T. So what is the trace of the stress tensor? Well, that's just minus rho plus terms which are order phi. And on the right-hand side of Einstein's equation, we're going to work to order phi to the 0. So what does that tell us? That tells us that R is equal to kappa rho plus terms which are higher order in phi, and T00 is equal to rho. So we can then proceed to write out the various components of Einstein's equation for various values of mu and nu. Now, the only non-trivial Einstein equation is going to be the 0,0 component of Einstein's equation, where mu and nu are both equal to 0, because that's where the stress tensor is non-zero. So I'm just going to write out that component of Einstein's equation. And you can check for yourselves that all of the other components are going to be trivial. So the non-trivial, or the non-zero component of the equation of motion will be the statement that R00 is equal to kappa times T00 plus 1/2 G00 times R, which, if we work to order phi to the 0 on the left-hand side of this equation, is just going to be 1/2 kappa rho, because G00 is minus 1 plus terms that are subleading in phi. So what we need to do is then compute. So we have here something on the right-hand side of this equation, which is proportional to rho. So just keep in your minds the fact that we're trying to compute, we're trying to rediscover the Newtonian equation for the gravitational potential. So we're already doing pretty well here. We have something on the right-hand side proportional to rho. R00 involves the second derivatives of the metric. So in particular, it involves the second derivative of phi. So all we need to do now is compute R00, which is the trace of the Riemann tensor, R lambda 0 lambda 0. And we need to compute it to order phi. Okay, so the Riemann tensor is a combination of the derivatives of the Christoffel symbol and the square of the Christoffel symbol. So the first thing we need to do is compute the Christoffel symbol to order rho. So let me remind you what the Christoffel symbol looks like. It's this particular combination of derivatives of the metric. So if we stare at this for a second, and we remember what the metric looks like, So this was the metric. We can then stare at this and see what the non-zero components of the Christoffel symbol are. So the first thing that we notice is that the only components of the metric which have a non-zero derivative are the TT components of the metric, the 0, components of the metric. And the second thing we notice is that we're considering static configurations where phi is time independent. So in order to get a non-zero derivative over here, what we need is a term where we have g00, comma I, where we're taking the spatial derivative of g00. So there are only, if you stare at it, there are only two possible Christoffel symbols you can write down where that guy is going to be non-zero. So, for example, if you write down gamma with all three zeros everywhere, you're just going to be taking a time derivative of something which is 0. So you need to have two zeros and one I in order to get a non-zero Christoffel symbol. So what are they? Well, you have gamma I 0, 0. So what is that? Well, you have a Gij, which is equal to delta Ij, and you have a 1/2, but that is canceled. Yeah, then you have a 1/2 times phi comma j. That comes from this last term here, because you have g00, comma j, and then you have a -2 coming from here, which will cancel the minus sign there and the 1/2 there. Likewise, the term gamma 00I will be non-zero. What will that be? There you'll get just phi comma I. That's a similar argument because you have here it's going to be this term, which will be non-zero, and there'll be a minus sign coming from this guy, which is a g00. So that's eta 00 working to leading order in phi. So you'll have a minus 1/2 to cancel the -2 in the metric. And these are the only non-zero Christoffel symbols which I've written down only to order phi. Is that clear? Any questions on that? Okay. So now we need to remember our formula for the Christoffel, for the Riemann tensor in terms of the Christoffel symbols. So there'll be two terms involving the derivatives of the Christoffel symbol, plus two terms involving the squares of the Christoffel symbol. So the first thing that I want you to notice when you stare at this equation is that these terms involving the square of the Christoffel symbol will only contribute at order phi squared. So we can forget about them for the time being. They're important, of course, but when we're working to leading order in phi, these will only give you terms of order phi squared. So what we need to compute is r lambda 0, lambda 0. So we need to set sigma and nu equal to 0, and then sum over the possible values of lambda. So that will be r 0, 0, 0, 0 plus r I 0, I 0, where I runs from 1 up to 3. Okay, well, what's r 0, 0, 0, 0? Well, as you can see by staring at the equation, that involves a time derivative. And everything appearing in this metric is independent of time derivatives. So that guy's equal to 0. And all we're left with is Ri0I0. So that is di gamma I 0, 0, just from this first term here, which is plugging in this equation here, delta ij di dj of phi. Okay. There's a name that we usually give this particular combination of second derivatives of a scalar function. This is what we call the Laplacian of phi. So if you go ahead, plug this guy into here, and then plug this guy all the way up into our formula for the Ricci scalar, and then plug that guy into here, what do you get? You get that to leading order, the equation of motion g mu nu is kappa t mu nu tells us that grad squared phi is equal to 1/2 kappa rho. Which is identical to the usual equation of motion of Newtonian gravity that you learned when you were taking your freshman mechanics class. Grad squared phi is 4 pi g rho. And we learn one thing in this equation. We learn that that constant of proportionality kappa that we just introduced but hadn't really said anything about is nothing more or less than Newton's constant g. So kappa, the constant of proportionality appearing in Einstein's equation, is 8 pi times Newton's constant. So, just to conclude, we use the principle of general covariance, the conservation of the stress tensor, and the requirement that we reproduce the Newtonian laws of gravity to uniquely write down the equation of motion of general relativity. So the equation of motion of general relativity in the presence of matter is known as Einstein's equation. It's g mu nu, which I remind you is r mu nu minus 1/2 g mu nu r, is equal to 8 pi times Newton's constant times the stress tensor t mu nu. So, are there any questions on this? The computation of the Einstein tensor for this weakly curved metric is the sort of computation that you should become very familiar with. It's an important class of computation, and it's one that you're going to have to do in one context or another many times in the problem sets in this course. Any questions? So, I would like to now spend a few minutes discussing Einstein's equations and letting you know a little bit about what sort of techniques we're going to use to solve and approach Einstein's equations in the remainder of this course. So, the first thing that I would like to do is I would like to write down for you a slightly modified version of Einstein's equations, which is sometimes technically a little bit easier to solve. So, as we did in our discussion above, you can take the trace of both sides of Einstein's equation. And what do you get? You get minus r on one side. That was just r minus 2r, as we described above, is equal to 8 pi g times the trace of the stress tensor. So you could plug that in and write down Einstein's equation for the Ricci tensor rather than the Einstein tensor, and you would get 8 pi g times t mu nu minus 1/2 g mu nu times t. So this is a completely equivalent version of Einstein's equation, which is sometimes called the trace-subtracted Einstein equation. This is equally correct as the original Einstein equation. Sometimes it's useful because that way you don't have to subtract off explicitly this correction term appearing in the Einstein tensor. So now what I would like to do is just make a few comments about the Einstein equation. So the first thing that I would like to point out is that you should think of this as a set of 10 second-order differential equations for the metric. So the metric is a symmetric 0 to 2 tensor. It has 10 degrees of freedom, the same number of components of a 4x4 symmetric matrix. The Einstein's equation, as we have written it, is an equation for a symmetric 0-2 tensor. So we have 10 second-order differential equations for the 10 degrees of freedom in the metric. So we have one second-order equation of motion for every dynamical variable in our system. So this is similar, it's the same order of difficulty, the same structure that always appears when we study dynamical systems in physics. We have one second-order differential equation for each degree of freedom. The only difference here is that now our degrees of freedom can be identified with properties of spacetime itself. Just as in Maxwell's equations, you can view that as 4 differential equations for the 4 components of the electromagnetic potential, namely the electric potential and the vector potential AI. You should view Einstein's equations as a somewhat more complicated version of that same sort of differential equation. The second comment, it's just something that I would like to emphasize, is that by construction, this is a tensor equation. And so it's an equation which is true in any coordinate system. And much of the art of solving Einstein's equation involves finding a coordinate system where it takes a simple enough form that we can solve it explicitly. And so much of what we will do in the remainder of this class will involve a judicious choice of coordinate system in one way or another in order to make this apparently horrific set of differential equations become relatively easy to solve. I should point out, though, that unlike the field equations that you have encountered so far in your lives as physicists, Einstein's equations is, in a sense, qualitatively more difficult than either Maxwell's equations or the equations of motion of Newtonian general relativity. So, sorry, Newtonian gravity, not Newtonian general relativity. So unlike, for example, Maxwell's equations, or the equations of Newtonian gravity, Einstein's equations are nonlinear. So, why are they nonlinear? Well, just schematically, the left-hand side of Einstein's equations involve the Ricci tensor and hence the Riemann tensor. And what does the Riemann tensor involve? Well, there's some terms involving first derivatives of the metric, which are first derivatives of the Christoffel symbols, which are second derivatives of the metric. But there are also terms involving the square of the Christoffel symbols, which means that they're squares of the first derivative of the metric. So there are terms in Einstein's equations that look like the metric squared, or derivative of the metric squared. So that means that the equations of motion of general relativity are not linear in the metric. That has a very important consequence for the structure of the solutions of Einstein's equations. What it means is that you can't just add two solutions of Einstein's equations together to get another solution. So, for example, if G1 and G2 are solutions of Einstein's equation, then that does not imply that G1 plus G2 is a solution. This is very different from Maxwell's equation, for example. If you don't have any charges present, you could write down one solution of Maxwell's equation and add to it another solution of Maxwell's equation, and you would get another solution of Maxwell's equation. Even if you have charge, if you take one solution in the presence of that charge, you could add another solution of the source-free Maxwell's equations to obtain a third solution with charge. All of your favorite techniques for solving differential equations rely in one way or another, at least many of your favorite techniques for solving differential equations rely on the fact that the equation is linear. For example, decomposing using Fourier analysis relies on the fact that you can decompose into Fourier modes and add them up together. The method of Green's functions, which you use to find solutions of Laplace's equation in Newtonian gravity or Maxwell's equations in electromagnetism, also implicitly assume that your equations of motion are linear. When you have a nonlinear equation of motion, life gets much more difficult. So it's worth stepping back for a second and asking why it is that Einstein's equations are nonlinear, whereas Maxwell's equations, for example, are linear. So why is it, let's ask ourselves, that Maxwell's equations are linear? Well, Maxwell's equations are linear because the source term in electromagnetism involve the charge of an object. Electromagnetic fields are sourced by charges. And the electromagnetic field itself does not carry any charge. Photons are not charged. So electromagnetic fields do not carry charge. But in general relativity, the situation is quite different. The Einstein equations are nonlinear because curvature is sourced by energy. And everything has energy, including gravity itself. The gravitational field, or gravitons if you want to use fancy language, themselves will have energy and hence will act as a source of gravity. So gravitational fields have energy, just like everything else. A photon does not have charge, but a graviton has energy. I should actually mention that there are more complicated versions of Maxwell's equation where photons do carry charge. They're known as Yang-Mills theories, and they are the theories that describe the elementary particles. So in fact, when you describe forces between elementary particles, either the strong or the weak force, you actually you do study theories that look a hell of a lot like electromagnetism, except that you have one, more kinds of charge, and two, the analogs of photons carry charge themselves will carry charge. So when you study Yang-Mills theories, for example, you also have to confront these same nonlinearities that we are encountering in general relativity. So what does it mean that the equations of motion of general relativity are nonlinear? What it means is that solving the equations of Einstein's of general relativity is hard. And so, because of that, there are relatively few examples where the equations of motion of general relativity can be solved exactly. So, when will we be able to solve the equations of motion of general relativity exactly? Well, generally speaking, the only time when we'll be able to solve the equations of motion exactly is if there is some symmetry present. So if you have enough symmetry, of course, that will simplify the equations of motion and allow us to solve the equations explicitly. The other time that we'll be able to solve Einstein's equations is in an approximation. So, for example, if you work in the case where space-time is very close to flat Minkowski space, then you can take all of your equations and work only to linear order around Minkowski space. And then it's actually possible and not too difficult to obtain approximate solutions. And the third case, where one can obtain solutions to general relativity, is if one uses numerics. Now, in this class, we won't be looking for numerical solutions of general relativity, but we'll use both of the two other strategies in order to obtain solutions. In our study of the Schwarzschild solution, which is the most important solution of general relativity after Minkowski space, we will assume that we have a certain degree of symmetry. And also in our study of cosmology, we will need to assume that the universe has a certain amount of symmetry in order to make the equations of motion tractable. And in our discussion of gravity waves, we'll find that we can only explicitly describe, we'll find the easiest way to explicitly describe gravity waves is in an approximation where the gravity waves are small ripples of the space-time metric, which is very nearly flat. So both of those two strategies will be important to us. And as the time comes, we will develop exactly what we mean when we say that space-time has a symmetry and how that helps us solve Einstein's equations. And we'll also describe in more detail the approximation techniques that we'll be using in the study of gravity waves. So, we really now, I think, this lecture and last lecture really form, I think, the core of this course on general relativity. So, we've spent about 3 or 4 weeks developing the mathematics of curved spacetime, and we've now understood how to do physics in curved space and what the basic equations of motion are, which will allow us to determine the curvature of spacetime in terms of the amount of matter present. So, for the next 2 lectures or so, what I would like to do is undertake a slightly deeper and somewhat different approach to Einstein's equations. And rather than diving in directly into the solutions of Einstein's equations, what I'm going to do is present an alternate technique for the derivation of Einstein's equations, which will allow us, in particular, to understand a bit better why Einstein's equations take the form they do, exactly what a stress tensor is and how we compute it, and why the cosmological constant is an important and interesting term to consider in Einstein's equations. But then, once we've done that, we'll continue to understand how it is we can solve Einstein's equations. I'll give you a little bit of a discussion of what it means for space-time to have a symmetry and what the implications are of that before proceeding to solve Einstein's equations in the most important non-trivial case to derive what is known as the Schwarzschild solution. And that will lead us to a discussion of the basic experimental tests of general relativity. Before, in the last few weeks of this class, we head on to study a variety of special topics, including black holes, cosmology, and gravity waves. So that is where we're going in this class. Let me just pause here and see if there are any questions or comments. Yes?
When we calculated the Riemann tensor I0 by 0,
yes.
why was the fourth term 0?
The fourth term was order phi squared. Right? We're working to order phi. Right? So what have you noticed? What you have noticed is that, let's scroll up and take a look at that equation for a second. What you've noticed is that, of course, this fourth term here was non-zero. So there are terms there involving phi squared. So what have you seen? What you have seen is that the actual equations of motion of general relativity are not exactly Newton's law of gravity, but they involve terms that are not linear in phi. So when we were working at linear order to find the equations of motion of Newtonian gravity hiding inside Einstein's equations, we were neglecting all of these nonlinear terms. But, of course, those nonlinear corrections are there. And they will have a lot of very interesting implications. For example, when we compute the gravitational field or the metric around a static spherically symmetric object, we'll find that it's not exactly given by Newton's answer. It's given by something else. It's given by the Schwarzschild solution. It's very similar in character to Newton's answer, but it's also different in some important ways. And the nonlinearity is one of the signatures of that difference. So yes, we were only working in an approximation scheme where we expanded the equations of motion to lowest order in phi. Good question. Other questions? No other questions? Okay. So, the next topic that I wanted to discuss was the Lagrangian formulation of general relativity. So, our strategy so far in our discussion of Einstein's equations was basically to guess the equations of motion based on some general principles. But as you learned in your mechanics classes, for most classical systems, and general relativity is a classical system, the equations of motion can be derived from a Lagrangian. Now, you are, of course, most familiar with the cases in elementary mechanics where you have a finite number of degrees of freedom. So, for example, if you have a single degree of freedom, say q, that is a function of time, then you can define an action which depends on q of t. So it's a functional of q of t. That is the integral of some Lagrangian that will involve q, its first derivative, and possibly time. And then the equations of motion come from extremizing this action as a function of all paths q of t through configuration space. And the equation which one must solve to minimize this action functional is known as the Euler-Lagrange equation. Which is often just written the variation of s with respect to q, and is equal to the derivative of the Lagrangian with respect to q, minus the time derivative of the derivative of L with respect to q dot, which has to be set equal to 0. So this is the Lagrangian formulation of theories of mechanics with a single degree of freedom. This single degree of freedom is a function of time, but general relativity is a field theory, just like electromagnetism. And a field theory is a theory with one or more degrees of freedom per point in space-time. So, whereas in a traditional mechanical system, you have one degree of freedom, for example, that depends on time, but not on space, in a field theory, your basic dynamical variable is a function not just of space, but of time. So, for example, you could have a Newtonian potential, an electromagnetic potential, which is a one form, or a metric, g mu nu, which itself depends on t and x. So these would be cases where you have 1, 4, and 10 degrees of freedom per point in space-time, respectively. And so what we seek is an action principle. So we wish to derive the field equations using an action principle So, for example, in general relativity, we will seek an action which depends on the metric of spacetime. So it's a functional of the metric of spacetime as a function of 4 variables, unlike in standard mechanics where the q, for example, depend on 1 variable t rather than 4 variables phi, such that if we minimize the action functional with respect to the metric, we obtain Einstein's equation. So we wish to take the variation of the action with respect to the metric and obtain Einstein's equation. Which will then be set equal to 0 if we extremize the action. Now, in mechanical systems with a finite number of degrees of freedom as a function of time, the action will take the form of the time integral of the Lagrangian. And so you might then ask how we're supposed to generalize this to theories whose variables are functions of space and time. And the answer is that for most field theories, the action is a functional, which will be a local integral. So it'll be the integral of some function which depends on g and its various derivatives. So it's not the case that every field theory has an action which can be written as an integral d4x, but only the case that some field theories can. Field theories with this property that the action is the integral of a function of points of space-time are known as local field theories. Happily, all of the field theories, Newtonian gravity, Maxwell's theory, and Einstein gravity, are all local field theories. So that makes it particularly easy to use general principles to determine what the action of the theory is. It's time to end class, and so your homework problem for next time, not graded, just something you should think about, is to think very carefully about the various principles you know about physics and tell me what the action of general relativity is. So there is a question. Yes? What it means is that the action is an integral d4x of something. That's what it means. There are other things that it means, but from the point of view of this class, let's take that as the definition of a local field theory. Another thing that it means is that the equations of motion of the field theory are differential equations at a given point in space-time. So, for example, you could imagine some other sort of theory where which relates the derivatives of various fields at different points in space-time. That would be a very strange field theory, and the standard theories of physics don't have that form. All right, see you next Wednesday. This Wednesday, I mean.
What's the ratio?